Hi, everybody. How are you doing? Good, I hope. All right, let's start. So today we finish operation on set, and we start order pairs, and it's going to go slowly towards a linear model. So the class is well organized, but the book is well organized because we slowly drift from first principles, which are sets, and we sort of build the whole edifice of mathematics that's useful for economics. So it really looks natural in a way. Okay, questions before we begin? No? All right. So let me share my screen. So I've posted what we've done so far. One thing I wanted to say is, the risk. So it's just my second time teaching this class, and sometimes I'm still asking myself questions about the material. And so last time so what I did essentially, I realized I read a bit further and it doesn't work. So associativity works with a single operation at a time. So you cannot have union and intersection and look at associativity. So that's why we discovered that it doesn't work. But here is one last law which does work. But yeah, still it's good to dig to put our try stuff and see how it works, just to get a feeling for ourselves. So associative law, that's going to be the last one. I'm going to start with an easy version of it. So let's look at purely so just the same operation. So assume sets A, B, and C. So we have distributive law is A, so union, for instance, union C. So what the distributive law says is I can distribute this operation onto each element of the union, and I can have the union between B and C after I have made the union with A, and it's going to give me the same thing. So this should give me A union B. So the operation with the set B, union A union C. And so we can pretty much imagine that this works, because all we get from this set of operation is the elements that are common to the three sets. Here with these, we get the elements that are common with A and B, and with A and C. So of course, oh yeah, no, not intersection, union. So here we fuse all the elements of B and C, and we fuse them with A. So we get a big set with everything that was in the three. So of course, if we do this with A and B and then A and C, so anyways, A is redundant. We already included it here. So if we include it here, it works too. So with union. And with intersection, it works too. So here, what we get is only the common elements of all three sets. So again, if I take the common elements of A and B, common elements of A and C, and then I can take the common element of these two new sets, then of course, I'm just going to get, again, the common element of the three sets. But what may be a bit more puzzling is combining the two together. So does A union B intersection C give me A union B intersection A union C or not? So I'm going to put a question mark here, but you may guess from what I wrote last time what the answer is. Do I have a guess? Yes, it works. And I can do the opposite. So let's start with that one. A intersection B union C is A union B intersection, oh, sorry, A intersection B union A intersection C. So first time I saw this, I thought, okay, that looks neat, but how do I see that? How can I wrap my head around it? If you cannot, then you're human. That's normal. So it's just so abstract to think about these things. So if you're very, very smart or have a very good way of thinking in abstract terms, then maybe you can think and see how these things work. But for just a question, will you tell? So yeah, I won't give you any exercise from the book. What it is going to be is what we learn in the class, what you do in TA sessions, so I will give you tons of exercises. But if you want to further your understanding and do exercises in the book, that's perfect. How you have to know which exercise to try is so follow the material I see here, and you can pretty much see which exercises are useful, because the class is built on the book. It's just that it's a subset of all the things that you see in the book. All right. So how can you see that? Well, there is one way to do it. It is using Venn diagrams. So illustrating properties of sets using Venn diagrams. So let's do that. Let's do it for a difficult one. So for this one, for instance, so anytime I want you to illustrate something or prove something, then please put enough steps in it and be precise enough that I can know, okay, from this to this, this is what was done, this is what was done. And so you have to start with the beginning and end up with the answer, and then start with the beginning again and end up with the same answer. And that's how you show that they are the same. You cannot just say, yeah, this is equal to this and just put one step. So that won't do. So yeah. Okay, so a word about proofs. Justification. Proofs. Yeah, so this is a best illustration. Don't do this. So some of you may have seen this before. So yeah, so here's a professor that wrote all his great proof, but then there's this step 2 there, then a miracle occurs. And so this is me grading your exam. And if you do something like this, I'm going to say, I think you should be more explicit here in step 2. So you have to be explicit about what happens. But I know it's normal when you think, okay, I'm not too sure how to show it, so let me start by the first 1 or 2 steps and then finish by the last step and sort of have some magical thing that happens in the center. Hopefully I don't see it. So yeah, you can always try, but I'm not going to get fooled easily. So be clear. All right, so let's do that with let's do it with Venn diagrams. So let's start with this one there. A union B intersects section C equals A union B intersection A intersects union C. So I'm just going to. So I'm just creating some blank PDF. All right. So I'm going to share my screen there. Okay. So imagine I have 3 sets. A, B, and yeah, this one I don't like. B and C. So that's a Venn diagram. If oops. Ooh. All right, so they're named after the mathematician, I think John Venn, but he himself named them Euler diagram because everything was done by Euler at some point. So Euler was a great famous Swiss mathematician. But yeah, we call them Venn diagrams. So I have set A here, set B, and set C. Yeah, these are a bit small. I don't know if I can, what's going to happen if I try to paste stuff. Oh, yeah, that works. Neat. Okay, it's still small. All right. A union B inter C. So let's start with this. So what is B intersection C? So it's this section there. So this is B intersection C. So you're clear that what you're showing me there, that's the common elements between the element between sets B and set C. And then if we take the union of this with A, we get, so let me try to copy everything. That's, oh yeah, I can't. I had to reproduce this. See? Yeah, so exactly. I'm going to say, please illustrate this with a Venn diagram, or I might say, please verify that it works for this example, in which I would give you some values for set A, for set B, and for set C, and you just have to make sure that the law or the property applies in that case. So how would you really prove something like this strictly? So what mathematicians would do is you have to show that some element of in each set, some element of that is part of set C is also part of set B and part of set A. So you really have to be strict. So I don't think Venn diagram would count as a formal proof for professional mathematicians, but still it's quite convincing. Yes, exactly. So, but I'm not going to spend too much time on the formal method because it's, I'm here to help you think about mathematics for economics, not to show you formal proofs. Anyways, I haven't looked at it too deeply. Yeah, still, I think it's possible to look at what we're doing there and deduce the way you would argue with a more formal approach. But here, this is good enough for us. All right, so then I have this, and this is going to be A union B intersection C. So that's this plus this part, of course. So that's what we get. Now let's try the second way. And this is always too small. All right. Yeah, actually, I would have to do two separate things, right? A union B. Yeah, okay, no, I'll do it. I'll do it I'll show A union B and A union C there. A union B and A union C. A union B, that's going to be in red. And A union C is going to be in, let's say, yellow or green. Oh, that's a bit too pale. So let's use, yeah, green. All right. So A union B is, oh yes, this is A. This is C. Yeah, so this is the kind of thing that would take less time on the board, but here we are. So A union B is this. Okay, it's not easy to. So that's A. That's B. And then A union C. Yeah. I didn't expect it to be so hard, sorry. All right. Okay, A union B, A union C, and then the result is exactly the same. So I'm just going to. And how do we see that it's the same? Well, we take the common values of the two sets. So I have this set here and this set here. So the common values are, of course, the set A, which is in the two subsets, and this intersection between B and C, which is in the two subsets too. So this is how you would do it to, well, hopefully you can draw a bit better than I did, but this is the kind of thing I want you to do. So to show me clearly what is what, so I can follow your reasoning. Otherwise, I would be lost. All right. So just for fun, so do it on your own for the other one. So let's copy all of this thing. That one, right? So I'm not going to say proof, I'm going to say illustration with Venn diagrams. So as exercise, try the other one in your own. Yes, so I've said that a bit last time. So I'm not here to torment you. I'm here to help you as much as possible. So, but economists do have to have a certain degree of formalism in their demonstration and their when they say write scientific articles, for instance. So you may encounter them. And in mathematics, in higher degrees, that's everything is about proving stuff. So what are we going to do here? Mostly illustrate properties and develop tools to help you optimize, to help you manipulate matrices and linear systems and all of this. But I am going to sprinkle on top some elements of proofs just to open your mind a bit. And so just so that you don't freak out, in the last time I taught the class, so maybe my proofs were too easy, but yeah, these questions were very well done by the students, so that wasn't a problem for them. So of course I could ask you impossible things to do, but I'm going to ask you to show very simple things. So simple things that are just extensions of what I may tell you is something like, okay, use Venn diagram to illustrate not this, but this, for instance, or this, for instance. So it's once you know how to do it for one, then you pretty much can guess that it's going to look like much like the same thing for the other. Is that convincing to you or reassuring? All right. So where were we? All right, so another thing I may ask you is example. So A is a set like 1, 3. B is a set like 3, 4, 5. And C is a set equal to 1, 4, 7. Yeah. So show, for instance, yeah, or show that the distributive property and let's pick one. We've already used that one, so let's pick that one for fun. Is applicable. It's these sets. So what you have to do is show me what you get with this and show me what you get with this, and of course that they are the same. So let's start with the first one. So A union B, inter B union C. Let's start with what's inside the parentheses. So that's, well, we can substitute all of them. It's A. C. So union, what's common? 1 is not common, so get rid of it. 4 is common, 3 is not, 5 is not. So there's only 4. If I'm not mistaken, right? Yeah. And then, oh no, yeah, sorry, I've taken the intersection again, but that's union. So that's 1, 3, 4, 5, and 7. Yeah. And then So intersection with 1, 2, 3. So what's common? There's 1 that's common, 2 is not, and 3 is. So 1 and 3. So that's one way to do it, and then the other way. Oops. Don't know how that happened. A, B, C. Right. So let's do what's inside the parentheses. So what's common between 1, 2, 3 and 3, 4, 5? That's only 3. Then common with 1, 2, 3 and 1, 4, 7. That's 1. This is okay. All right. And if I take the union of these two, then I get 1 and 3. So that's something I could ask you to do. Yeah. No, not empty. If I got empty there, that would mean that everything I've been teaching you so far is a lie, and that I cannot be trusted as a teacher. So yeah, that wouldn't be a good state of affair. All right. So let's try some other examples. So imagine I take no, okay, I'll just leave it at that, but give you some exercises too. So yeah, so I've prepared some quizzes that you can do online. So I'm going to give you the address. So, or I can write it, yeah. So here you can get it, or I can write it there so you can just wait and see it for yourself. So I'm just going to share my screen and show you what that looks. Yeah, so I have some quizzes about sets, so you can try them on your own. And what I think I'm going to do is not take time during this this class to let you do it, because some of you may be very quick, others may take more time. Yeah, so you can do it on your own after the class, and then the next class I'm just going to look at it briefly during class. How about that? No, it's not graded. That's just for your own education. But so know that thing though, if you don't do it and then I comment on it in class, then it doesn't help you at all. So you have to try it on your own to understand it, to see what is difficult about it. Oh, I thought I did, sorry. Okay, no, I did it in a private message, that's why. All right. Yes, it looks like this. So this is just to show you that we don't have to use numbers all the time. We can use anything. So here I've used emojis if you like animals, and snakes, and letters, and rabbits, and beers, all these things. So just some exercises and sets. Yeah, about the answers. So I think at the end you can know where more or less if you got it. plus, yeah, so I think you can know if you got it, and you can try as many times as you want until you get it perfect. Plus, I'm going to give the answers next class. Okay, and then you submit it. So yeah, you get plenty of time to practice. There's just no way around it for anything that's math related. It's a muscle, so the more you practice, the better it is. So I had a teacher who always said, did you have to do much algebra for this class? Good, that's good for your health. So if you don't want to catch COVID, do some algebra, you're going to be healthy. Yes, or maybe one, maybe even 2 per class, or maybe no per class. It depends. I have made a bunch of them, but maybe I'll add some others. We'll see how it goes. But I post exercises to do too. So these small quizzes are something that I've just added, but you also have TA sessions. All right. So going back to this. Oh yeah, I was back. Okay. So next theme, relations and function. So that's a big one. Let's see, that's a big section. All right, relations and functions. So again, a bunch of definition, ordered pairs. Are there questions about what we've seen so far with this? No. Anyways, if you think about something that was unclear, just ask. That's fine. So as we have been saying, so in sets, the order of elements does not matter. In ordered pair, as the name suggests, or sometimes you may hear tuples. The order does matter. So for instance, if you have the set 1, 2 is exactly the same as the set 1. Here, I'm going to write them with parentheses, as I should, as you will have to. So this doesn't equal. All right. So this is a set. This is a set. This is an ordered pair, and an ordered pair has its elements that in order. So 1, 2 is not the same as 2, 1. So the first place represents something, and the second place represents something different. So it has to be that I have the same thing in the first place and the same thing in the second place, or third place, or whatever. So how many I have. And an example of ordered pairs, coordinates. So here it's not, maybe it's not pairs anymore since I have more than 2. So XYZ. So for instance, this may represent it's maybe 1, 2, 3, or things. Like animal, number, equals, and then I would have something like Doug and 4. Or I could have, if it's a data set, for instance, so you could have, I don't know, demographic characteristics. Like, for instance, age and city. So you see that this could be in a data set of, that you would use in a statistics class, for instance. So that would be 18 years old or 19 years old and Montreal. Right. So of course you cannot flip these. So 19 and Montreal isn't the same as Montreal 19. Because anyways, Montreal isn't an age and 19 isn't a city. But still 19 can be a word because now we have COVID-19 as an official word. So, and for taking the example of, so I'm not going to take time to write it because it's kind of obvious. So if I have like this. Yeah, that's a bit small, but you can see. So in a set, the index of the number wouldn't matter. Yeah, yes, because in a way you don't have an index per se. So you can think of a set as just a bag of stuff. So you don't, it's not like, oh, there is a specific pocket for one and the other and the other. It's just, you can shuffle the bag however you want. All you care about is what's inside it. So there's no index. Yeah. No, in an array that clearly matters. Yeah. Because in an array, then there's one location for everything. So, okay, if we go on the terrain of computer science, then, so what you're asking is how should we represent in computer memory sets or sets or tuples, for instance, or ordered pairs or other things, then of course, probably you would all represent them as, well, it depends. So if it's an array, then you could just represent them as a set of location in memory that are all contiguous. But if it's an ordered pair, like you have one matrix and one number, then of course you cannot necessarily write the matrix in one spot and the number just after. So you could have pointers to one of them. So sorry for the non-computer scientists in the room. Yeah. Okay, so that's why you cannot, so that's why, of course, these two things are different. Cartesian products. So you write this like this. So that's a weakness of mathematics, is everything is overloaded with meaning. So this, you may sometimes see this as representing just multiplication if you have two scalars, like 1 times 2 equals 2. So you may have seen this when you were in school, but in that case, the Cartesian product has a specific meaning. So I'm just saying I'm using this symbol as a representation of the Cartesian product. So is the set of possible ordered produced by the elements of two sets. So for instance, A equals, let's use always the same, 1, 2, 3. And B is 4, 5. Then we write A times B equals to a set. So it is a set. So it's an operation between two sets that give me another set. But in the first case, it was made of some elements. And then what I'm going to get is ordered pairs of these two elements, which will look like this. So I'm going to get 1, 4. So let's just, I'll write the same and change it afterwards. That wasn't clear. So 1, 4, 1, 5. 2, 4, 2, 5. And 3, 4. And 3, 5. This is superfluous. So did I make a mistake somewhere? 1, 4, 1, 5, 2, 4, 2, 5, 3, 4, 3, 5. Yeah, that makes sense. All right. So question. Does A cross B equal B? I don't know how I should pronounce it, times or cross or X or whatever, or Cartesian product. So does A Cartesian product B equal B Cartesian product A? What do you mean for a set? Yeah, okay, so Mr. Wang's answer is the right one. So no, because if I do B Cartesian product A, then I get all the elements of B in front and the elements of A after. So I get ordered pair, but with the elements flipped. No, because the ordered pair would be reverse order, which will not do because they are ordered pairs. So they must have the same order. Question. If A has M elements and B has N elements, how many will be in A times Okay, so the question is, would it be yes for a set? I'm not sure what this means because, so A is a set, B is a set. So it's a set, and A times B is also a set. So these are all sets, but the elements inside in A times B are not sets, they are ordered pairs. So as long as you, are you sure that's M exponent N? So let's try it with that one. So I have, yes, 8 times N, M times N, but here it's multiplication. So it has M times N elements. Yeah, so, but since M and N are scalar, then maybe you can write M cross N. So that's the difficulty with math, is that yeah, everything has different, some things have a unique meaning, but yeah, we don't have an infinite number of symbols, and sometimes it's confusing. Oh, that goes beyond what I know. So so yeah, so if something is an ordered pair, then it's written in parentheses, right? And yeah, and if something is a set, then it's written in brackets. So that we know. Now this symbol, I'm going to always use this symbol, and I'm going to say in the question, I'm never going to write what is A times B without telling you that I want to make to get a Cartesian product, that A and B are sets, for instance, because you would perfectly you could say, well, maybe A is a scalar and B is a scalar, and this is just a normal scalar multiplication, so that way you wouldn't know anything. So yes, I'm going to give as much detail as possible. And by the way, so that's so good exams are exams that are clear with enough details, but they may be some. It's not like it's super easy for us. It takes work to make sure that there's no second interpretation, because when you explain something, then for somebody it might mean something, but for somebody else there can be a hidden second meaning that you hadn't thought about, and then you have to deal with it later. So yeah, I'm going to make sure that everything is clear in the exam. All right. So now, why do I introduce ordered pairs? Well, for Cartesian coordinates is useful, but so of course, what happens if I have infinite sets? So if I have the sets of, we need to cancel the repeated part. What do you mean? Do you mean here? Because I don't think there are repeated parts in ordered sets, because this is the set number 1 that I gave you, and this is the set number 2 that I gave you. So there's each element happens uniquely. 1, 2 times in this set. Oh yes, so whoa. Wow, I've never thought about this question before. So what happens if you have, can you have a set with 2 times the same element? I don't think so, but it's the first time. Yeah, I would imagine that for any sort of use case, you would never have this. it's like saying, do you have the real numbers, but then the number 2.5 happens 2 times. So that's doesn't make sense. Or it's like saying, so imagine that it's a set is something like, so if I say something like, okay, it's a multiple choice question. So you can answer A, B, C, or D. So the set of potential answers are A, B, C, D. So you wouldn't say something like A, B, B, C, D. Well, yeah, we know B is a potential answer. I already said it. So yeah, I don't think that would make sense. No, but it's a nice thing to ask ourselves. Yeah, and if it's a coordinate, then the coordinate matters. Yeah. If A and B are the same sets, then yeah, that's perfectly fine. So you would get like B. So example. So B times B equals. So what we get? We get 4, 4, 4, 5, 5, 4, and 5, 5. All awesome questions. Really nice questions. It's always good to explore the corner cases and the things that just to settle things, to make everything clear. Yes. So example, answers to a test. A, B, C, or D. Yeah, but that may open the, okay, I'm not going to put it there. Maybe it's going to create more confusion than I'm going to stick with that. Okay. Oh yeah, so then what if say A has elements 1, 2, and 3, but then what is if A has elements all the real numbers, for instance? How would you write this down? So sets with infinite elements. So I think it's with, so you would say it's infinite cardinality, but yeah, I'm not going to introduce vocabulary for no reason. So let's just stick with this. So for instance, if X is a set of all the real numbers, oops, and Y is also the set of real numbers, then X times Y is, so we're going to write it, we cannot, of course, write it this way because we have an infinite number of things to write. So what we would write is a description of the set. So it's a set of ordered pair, X and Y. So where X is element of, so I'm going to be more specific after, such that X element of R and Y element of R, right? And we write it. XY element of R times R, because that's what X and Y are. So XY element of R times R, or also element of R squared. All right. So this is where this formalism comes from. So when you hear it's in R squared, what you're saying is I'm looking at coordinates that can take any value in the real numbers, but so I'm looking at the Cartesian coordinates. Yeah, so by the way, come from René Descartes. And yeah, provide link between algebra and geometry. So sometimes you can say it's algebraic geometry. So Descartes has done many different things, but just this insight that if you think that about representing shapes like triangles, squares, circles, lines that we used to do by hand or draw, or we used to do proofs with them, but just graphical proofs. And then it's just a simple insight that, oh, if I set my things properly and I'm able to represent things in a 2D system, then all the geometric proofs that Euclid and all the others did before me, I can redo the same proofs and check them using algebra. So this is one of the most profound event in the history of mathematics. Really, that makes him one of the most influential mathematicians, even though he didn't produce anything as great as others like Euler or Gauss or Riemann. Yeah, so he was a philosopher too. He was many things. So, but just this insight that you can have a profound link between algebra and geometry is an awesome discovery. All right. So, yeah, of course, we can extend the Cartesian coordinate system to higher orders. So, example, XYZ element of R cubed, or simply. So I'm going to introduce some other notation there, but yeah, not really. So I'm just going to say X is an ordered pair of some number of elements in it. So I'm going to write X1, X2, Xn, which is element of Rn. And of course, it's not limited to the real numbers. So you could have something like Cn. So complex numbers in n dimension. And believe it or not, before doing economics, I did a bit of computer science, and there was a class in which it was just proofs on CN, proofs in CN. It's just my, I really hated that class. But yeah, you can do many proofs of things that are so general that they can apply for complex numbers in any number of dimensions. And useless to say that you're never going to have to deal with this thing. So at least in this class. All right, so still have a bunch of sometimes a straight line, a set of coordinate of ordered pair in part 2, satisfying a linear equation. So example, so what straight line can we take? So xy. So it's a set of ordered pairs, so x and y. So these are my first coordinate, second coordinate, such that they, so you could say xy is element of R squared, but usually when I don't say it, then you just assume that I'm talking about the reals. So for instance, y equals 2x plus 3. So here is, that's my straight line. It contains an infinite number of ordered pair. It's a set of all the pairs that verify this equation there. All right, so I might ask you to draw it, and hopefully you're not too rusty at it, because in economics we have to draw curves all the time, not curves, but straight lines all the time. So a trick to draw it. So what if, since you know it's a straight line because it has a constant coefficient linking y and x, then how many points do you need to draw it? Yeah, 2. So if you have 1, then you know one place in which it goes, but it could go to other places too. So you need 2. You need 2 points. So so need choice. So any choice will do, but x equals 0, x equals 0, and compute y, and y equals 0, and compute x. So we get 2 points. So let's do that. Oh, you did it already. 0, 1, and 1, 0. Is that so? So let's try x equals 0. So 2 times 0. So I get 3. So first point. Um, 0, 3. Then y equals 0, so I get 2x plus 3. So x equals 3 by 0. Oh yeah, minus. Yeah, that's right. Yeah, may that be the most fun example to draw, but here it is. All right. So let's go ahead and draw that. Oh, am I showing the right thing? I think, yeah. Okay. So I want 0, 3 and minus 3/3 0. Let's go ahead. So let's have some numbers on the graph. So this is -2. Oops, it's very small. -1, 1, 2, 1, -1. So the first one, oh yeah, and this has to go to 3. Okay, wrong. Can I save this? No.
Sir?
Yeah.
We can't see the screen. It's black.
Oh yeah, okay, sorry. What? That's funny. Now can you see it?
Yeah, now it's good.
Okay, good. Yeah, the fun of Zoom. We have to enjoy our last moments. Maybe at last we can go back in person. So okay, here we go. So first point 0, 3, so that's there. And second point will be -3/3, so that's here, and 0. Why is this so big compared to the other? All right. So if I ask you to draw some line, this is what you must do. So you show me where the points are, and yeah. So let me try and paste this in the document. Okay, so here it is. Yeah, so we're almost out of time. Do I have something to add? A few minutes left. Yeah, I could talk about inequalities for a bit. So if I had the same thing, but instead of equal, I had something like greater or equal. So how would what would that represent? Would that be a line? No, that would not, because here all the points that are above 2x plus 3 are verified. So we can sort of intuit that probably it's since the y-axis is there, probably it's going to be up there. But in case we're not sure, in case you're wondering how you draw it, so trick to draw it. You try some point, not on the line. Let's see whether it verifies an equation. So here, for instance, let's try 0, 0. So I would have 0, 2 times 0 plus 3. So is 3 smaller or equal than 0? Yes. Okay, so yes. I think it means xy coordinate are not a function. Oh, this is so are you wondering what this symbol means? This symbol means such that. Does that make sense? So it's any point or any ordered pair xy such that this is true. Yeah, so does that make sense? 0. Oh no, so that's wrong. Yeah, so is wrong. So we know that 0, 0 is not in the set. So if we go back to our set, that would look like, and I'm just going to finish with this really quickly. So it means that the point 0, 0 is not in the set. So the points that we care about are up here. So I'm just going to try this really quick. So of course, it's not a triangle, it's the whole region, but we get the idea. All right, so I'm going to stop here unless there are other questions. Just to confirm what? Yeah, people have been asking me this too. See the latest update. Oh yeah, okay. So yeah, it looks like on January 20, which is yeah, so our next class is still in online. And then the class after that is in person. Yeah, I think so. So yeah, from the latest. Yeah, look at the book. In the book, okay, so just one thing. So from the latest info. Next time is online. Then next in person. And for practicing proofs, read the book. There are many examples. But there is one thing I want to say though about proofs is that it's very hard for me to say, oh, learn these 5 ingredients and you can write all the mathematical proofs in the world. No, there are so many different ways of showing so many different things in mathematics that I wouldn't feel like I could tell you do this or do that. So the best way to the best way to prove stuff is to look at how I did in the class and imitate as much as possible, or just think for yourself of a nice way to demonstrate something. Just using your intuition. I know that during the exam, that's the last moment when you can use your intuition. So that's why in the exam, I'm never going to expect you to be super creative. It's just a place to make sure that students who read the things well and did the exercise, they are conscientious, they do well, and that's it. Set A and B. So here you wrote A is 2, 2, but you wrote with parentheses. So did you mean to write a set or a ordered pair? If you want to write A is a set, then you would write A equals 2, and that's it. Because the element 2 is repeated, you don't need that. Plus you write it with curly braces. All right. So you would have A equals 2, B equals 2, and A, do I have my cross? A times B equals a set of, yeah, that's what we would write. I wouldn't say that. I would say that for Cartesian product is an operation on sets. Yeah. So you need that. So you need A being a set and B being a set to be able to have a Cartesian product of A and B. Okay, trying to buy the book online, but I cannot find it on the bookstore site. Oh, so I've at the library you can have a few chapters of the book for free, But otherwise, I don't know if you can get it at the bookstore. It's been edited so many times that you should be able to find it on say on Amazon, not too expensive. Yeah. I don't know how the Concordia bookstore works though. So. Okay, good for you. That's so get it online for free. As a teacher, I'm never going to say do that, and I'm never going to give you a link. But so do as you can. I cannot say that I've never done that either. So. So it looks like you have a resourceful person in the class. So if you want help, you know who to ask. But I'm not saying much else. I'm not encouraging. All right. So other questions before I go and I say have a nice weekend. No. All right. So okay. So have a nice weekend, everybody, and I see you next time.